Now in this video we are going to cover the properties of variance or something related with the variance. So we know that in our general notation the variance is, for the sample we know it is summation of x minus x bar whole square divided by n minus 1. And in matrix notation we have the variance of vector x, let me call it x, vector x, this is equals to x vector x transpose m0 x and divided by n minus 1, that is I transpose I minus 1, and where I is equals to the column vector of 1s, and here the sample size is 3. And let us take any arbitrary x with the value 1, 2, 3. So in this case we know that I transpose I should be equal to the sample size, I transpose x, this should be equal to summation x, and then m0, where m0, this is the deviation from mean matrix, this is I minus I transpose I. Now let us see the property related with this. Let us say summation of x minus x bar whole square, and let us expand it further. So what do we get? Summation of, this is a minus b whole square, it is a square minus twice a b plus b square, and let me write it as x square. And let us operate the summation rule. So this is equals to summation x square and 2 and x bar, or this means they are constant, so minus 2x bar, and we are left with summation x. We have used this summation to this, then after plus, and let us apply summation to this as well. And x bar is constant, so its square is also constant, and we're going to use summation x bar square. So if we further operate it, this is equals to summation of x square minus twice x bar, and then summation of x, we can write it as, there are n number of people and their average, let us say their average, this also is equal to the summation of x, because our x bar is equals to summation of x divided by n. Therefore when the sample is multiplied with their average, this is equals to the total value of x, and plus the summation of x bar square. So as this is the constant, and if we have n number of observations, then when we sum the constant n number of times, we get it n number of times the constant. So this is equals to summation of x square minus twice n, and then x bar square plus n x bar square. So this is equals to summation of x square minus n x bar square, because they are the same and we have to use simple operation. So this is what we get by x minus x bar square. And for the population, if we divide, if we take its average, this is, it will give the variance. So the variance is equals to the average of this part minus x bar square, or the square of the average. And in the case of sample, we divide this by n minus 1, and we are going to get the variance for the sample. And this is equals to, we divide this also by n minus 1, and n divided by n minus 1. So this is going to be very simple. Now let us calculate this relationship for the vector counterpart. So it is summation of x minus x bar square, and in the vector notation this is equals to x transpose, this is the vector, and then we have m0, because m0 is the matrix that gives deviation from the mean, and then it is x vector x. So this is equals to this relationship. Now let us say it is x bar, and let us write it in its original form. This is equals to I minus I transpose, and then I transpose I and x. Now let us operate it. First of all, let us multiply this with this as well as this, so we get it as x transpose I x minus, let us do the similar thing to this as well, I transpose, and then I transpose I x. So if this is the identity matrix, and we can write it as x transpose x. Now let us write it as minus, and this is x transpose, this is equals to I transpose x I, and here if we use this I transpose x, this is summation x, and I transpose I, this is going to give us the average of x bar. So this is equals to x transpose x minus x transpose I, if summation x is equals to I transpose x, and we have I this and x age 1, 2, 3. If this results in summation x, then this should also result in summation x 1, 2, 3. If we take the x transpose and then I, this should also result in summation x, they are same. And the summation x divided by I transpose I, here summation x means I transpose x, or we can write it as x transpose I divided by I transpose I, this is equals to x bar. Therefore here x transpose I or I transpose x, they are similar. This is equals to n I transpose I x bar. So this is equals to I transpose I x bar. From this relationship, this is equals to x bar and I transpose I. So I transpose I, this is equals to n. Where is our n? So this is equals to, let me write it as I transpose I and then x bar and another x bar. So this is equals to x transpose x minus I transpose I is equals to n, and this is equals to x bar square, and we get the same result in matrix notation as well. So is our x is of order 3 into 1. So x transpose x, this is of order 1 into 1, and this is also of the order 1 into 1. They are scalar. Therefore, summation of x minus x bar whole square, this is equals to this result. So this is our vector counterpart. So let us assume a variable x. So it has its mean age x bar and the variance age s square. And we construct a variable y such a way that we scale the variable x by a and then we shift its origin by b. So we have already seen in our previous video that the average also follows this rule. So the average of y is equal to a times the average of x and plus b. So this is the result. And if we subtract both of them, y minus y bar is equals to, our a is common, x minus x bar plus b minus b, and this is 0. Y minus y bar, this is equals to a x minus x bar, because this is 0. Now let us square this. It is equals to y minus y bar whole square. This is equals to a square and then x minus x bar whole square. And if we take the sum on both the sides, y minus y bar whole square is equals to a square. This is constant, that's why I've taken it outside of this summation, and x minus x bar whole square. And if we divide both the sides by n minus 1, so what do we get? This is n minus 1 and this is n minus 1. So the variance for the sample, the variance of y is equals to a square the variance of x. So this is a very important property. The shift in the origin, that does not matter, while the scale factor, this is going to be squared, this relationship in terms of its variance. In other words, the scale is going to affect the variance while the origin is not going to affect the variance. So let us see an example. So if we have 4, 3, 2, so the variance of this is not going to be affected whether we add or subtract any value, any constant value. But to this 4, 3 and 2, if we multiply it by some constant, then the variance is going to be a square times the variance of this original, let us call it as x. Prove the same relationship making use of vector notation or matrix notation. In fact, let us use the vector notation. First of all, let us write the relationship in terms of vector notation. So y, this is a vector y, is equals to a times the vector x plus I and b. Because in vector notation, b is a constant and we need to write so many number of ones. It's for the number of observations and we multiply it by b. So let us, and we know that m0, this is the matrix that gives the deviation from the mean. So let us multiply both the sides by m0. So this is m0y, and this is equals to m0ax vector x plus m0ib. Therefore, m0y, this is equals to a is constant and it is m0x plus b is constant. So this is m0i. Here m0i, this will be equals to 0, and let me prove it. So m0 can be written as m0 transpose because it is an idempotent matrix where m0 is equals to m0 transpose and m0 is equals to m0 transpose m0. We have already explained or proved this relationship in our earlier videos. And so m0 is equals to m0 transpose I, and then we also know that b transpose, this is equals to b transpose a transpose. So let us write it in this way. I transpose and then m0 its transpose. So if we operate this relationship, a into b transpose is equals to b transpose, so we will get m0 transpose, and then a transpose, so we get this result. And this is equivalent to as m0 is the deviation, it gives the deviation from the mean. So if we add the I transpose, this gives the addition of this. So we have seen that the deviation from the mean is equal to 0. So this is equals to 0. So m0i, m0 is equals to I minus I transpose I, and here we have our I, and let us multiply it. This into this is equals to I minus I transpose this I divided by I transpose I, and this is equals to I minus I transpose I, this is equals to m, and this is also equals to m. We can cancel out, this is I minus I, this is equals to 0. So here this term is equals to 0. So we are left with m0y is equals to a m0x. Now let us use m0y transpose is equals to, so as they are equal, so I'm multiplying this with this itself, multiplying this with this itself. So we're going to get a m0x, its transpose, and then a m0x. Now let us operate it. A into b transpose is equals to b transpose and then a transpose m0y. This is equals to a is constant, so it's transpose. It is immaterial whether we take the transpose or not. It is a, and a into b transpose is equals to b transpose a transpose. After a, again it is constant over here, so this into this it is a square, and we are left with m0x. And there are idempotent metrics. So this relationship, it is y transpose m0y. This is equals to a square and then x transpose m0x. And we know the variance in terms of a matrix form. So if we divide this by n minus 1 or even n for population and n minus 1 for sample, so let us divide it by I transpose I minus 1, and here also I transpose I minus 1, then this is equals to the variance of y. This is equals to a square variance of x. So through the vector counterpart as well, we derive the same relationship. So in the nutshell, if we change the origin of any variable, then its variance is not going to change. But if we scale the variable by certain factor, then the variance is going to be affected by the square of that factor. So this is it for this tutorial. Thank you very much for your time. Thank you very much. Econometrics Melody.